Hello, welcome to CannaLab. My name is Chris. Today I'll be discussing sample preparation and provide a brief overview of the potency methods we recently developed using HPLC. Following this brief presentation, I'll share a video describing the basic steps required for extracting cannabinoids from hemp flower. Let's start by discussing the overall potency workflow. This workflow consists of 4 basic steps: sample preparation, calibration, chromatography, and data analysis. So what are some of the highlights of this workflow that make it unique? We offer step-by-step instructions for sample preparation that allow for the analysis of 17 cannabinoids. We've developed 3 different methods depending on your HPLC instrumentation. The first being a rapid high-resolution gradient method, which is about 6 minutes on a C18 column, 2 micron particle size. The second is a rapid gradient method, also about 6 minutes on a C18 column of larger particle size. And the third method being a low pressure isocratic method, which is about 8 minutes on the C8 column. All of our methods utilize low flow rate for reduced solvent consumption, which leads to additional cost savings. And all of our mobile phases are compatible with mass spectrometry. Okay, let's go over the basic steps required for sample preparation. So the first step being homogenization. So we recommend homogenizing at least 5 grams of hemp flower. Using a cryomill is ideal because it generates the least amount of heat, and it's known that excess heat will break down some of the cannabinoids, which will kind of skew the true cannabinoid profile. Next, you want to weigh about 500 milligrams of homogenized material transferred to a container. Next, we perform a series of 2 ethanol extractions. So each ethanol extraction uses about 20 mils of ethanol. It's shaked for vortex for 30 minutes and then centrifuged to remove the insoluble plant material. Each extraction, you're going to transfer the soluble fraction to a 50 ml volumetric flask. And then once the 2 extractions are performed, you bring it up to volume with ethanol. Next, you perform a 1:10 and 1:100 dilution with methanol, and then next you filter your sample. There's also the option of filtering the sample after you bring it up to volume in the volumetric flask. The critical aspect of cannabinoid analysis is the preparation of your standards. The use of high-quality CRMs is essential for accurate quantitation of cannabinoids. Cerulean is an ISO 17034 manufacturer of CRMs. We offer a large variety of cannabinoids in solution format, carefully optimized for the highest level of stability and ease of use. Each product comes with a detailed certificate of analysis documenting the certified concentration, measurement uncertainty, and metrological traceability. We're constantly adding new cannabinoids and be launching cannabinoid mixes within the next few months. Here's an example of how one might prepare a standard mix containing the 6 major cannabinoids. Using the following dilution scheme outlined in this table, a calibration curve spanning 0.25 to 100 micrograms per mil can be prepared to accurately quantitate the major cannabinoids in a sample. We recommend preparing standards in an amber volumetric flask or gravimetrically to ensure the highest level of accuracy and batch-to-batch consistency. As I mentioned earlier, we recently developed 3 different HPLC methods that are capable of separating 17 cannabinoids. All these methods offer short runtimes, low solvent consumption, and mass spec compatibility. Additionally, all these methods use the same easy-to-formulate mobile phases, further reducing user errors. This is an example of the low-pressure isocratic method on the Synthesis Express C8 column and is compatible with a conventional HPLC system. Using a gradient on the Synthesis Express C18 column, we're able to achieve better separation of delta 9 and 8 for a total of 17 cannabinoids in a runtime of about 6 minutes. The rapid high resolution method offers the highest level of resolution and is well suited for a modern UHPLC system. Real-world testing has proven consistent performance across thousands of injections across several matrices. This high-efficiency column is well suited for handling additional cannabinoids in the future should there be a demand for 17 plus cannabinoids. Using two of the methods I just described, the low-pressure isocratic and rapid high-resolution method, where an orthogonal analysis was performed on hemp flower sample to determine the total THC and CBD values. Both methods were capable of quantitating the 6 major cannabinoids and also provided a profile of the minor cannabinoids. The results from both methods were in agreement, providing further confidence in the calculated total THC and CBD values. So next, I'm going to show you a video describing the basic steps required for extracting cannabinoids from hemp flower.
So let's talk HPLC instrument configuration. This is not the most exciting or appealing subject, but it certainly is relevant to you maximizing your instrument performance for the methods you are developing. So let's jump right in. So what we're going to cover first is instrument selection and column selection, and the two are interrelated, and that's an important point to understand. And again, I'll explain that further. We're then going to jump right into how to actually improve the instrument performance through the instrument configuration, the hardware configuration. This is really about minimizing system dispersion, although we're not going to go into the theoretical discussion of that. We're going to stick with sort of the take-home messages. And then data collection. There's some parameters of data collection that need to be attended to as well. So that'll be the contents of this talk. Not very long, pretty straightforward. So let's get started then with instrument selection and column selection. So why does instrument selection matter, or does it? Well, if you're going to attempt to use some advanced columns, newer technologies that require that you're going to want to maximize resolution and throughput, instrument selection then does definitely matter. You're going to have to pay attention to that. If you're going to be using traditional columns, and by that I mean columns that have 5 micron, maybe 3 micron fully porous particles, instrument selection is likely not critical. Particularly if you're using 5 micron, you're not going to have to be concerned about that. So it does really depend on what your strategy is around column selection. So in looking at your instrument options, whether this is what is currently available to you, or maybe even if you're looking at purchase, you have the sort of 3 classes of instruments that you can think of that you have options for. The first, is, the traditional HPLC. These were, at the most 400 bar instruments, as they were called. That's the maximum pressure. Though these were instruments that were around, more than 10 years ago, but, you can still find in labs, and I'm listing here simply just examples. It's certainly not comprehensive, but examples of typical instruments in each category. So for the traditional HPLC, probably the most common one in that case is the Agilent 1100, right? And again, just some other ones of that same generation as well listed there. If you're looking at new instruments, though, you're probably not going to be able to find anything less than what I'm calling an advanced instrument here. In other words, I don't think traditional HPLCs are sold anymore. These are ones that have a higher pressure limit, 600 bar. Again, one that came out that was very popular, of course, because as just an iteration of Agilent's product line was the Agilent 1200. There's the Shimadzu LC20, which was, also had the name Prominence that was fairly popular. And then there's the UHPLCs. These are instruments that can deliver, back pressures in excess of 1,000 bars, or at least 1,000 bars. And, the Waters Acuity, is probably the first one on the market. And again, here are just a couple other popular ones that you frequently see. The Thermo Ultimate 3000 actually is interesting because depending on how it can be configured, it can also be maybe shifted down into the advanced instrument. It's quite configurable. But others that are not listed here, I don't have the room. The Shimadzu LC30 or now the LC40, the Thermo Vanquish is their latest edition. So yeah, just think about sort of these 3 different classes of instrument. And because this is, I'm going to be referring to this in terms of column selection. And what I've also listed here above this, below the headings, is just sort of a diagram, if you will, a graphic of system dispersion. So that's really what has evolved here with the instrument evolution, is designing instruments that have smaller system dispersion so as to take advantage of higher performance columns. So, when it comes to column selection, I need to touch on, particle technology. And as I just said, this is limited to particle columns. There's the 3 to 5 micron porous, fully porous particles as what I consider traditional columns. Now, There are other smaller size fully porous particles for sure that gets you right into the high performance category, but in the context of traditional columns, we're talking about 3 to 5 micron porous particles, with emphasis really more of the 5 micron. Because of the larger particles, larger as in 5 micron, there isn't the highest resolution, and therefore also methods will tend to be longer. I mean, that's a principle, a very fundamental principle, that efficiency is related to column length. Because it's not the latest and greatest technology, of course, they're lower cost. So, that's certainly an advantage, if you will, or that's one of the trade-offs then, though, is performance. In contrast to that are 3 to 5 micron core shell or superficially porous particles, and in our case, in our product line, it's the trademarked fused core particles. These are higher performance columns. They're higher resolution and therefore require shorter methods. And the real advantage is that they deliver the highest efficiency per unit pressure. So as this diagram shows, you have this outer porous shell, thus the names like core shell or superficially porous, in which the material there has a porosity just like the fully porous particles, but much of the volume of the particle is actually impermeable. It's a solid glass, for instance. So it's only the outer layer that is accessible to solvent and thus the analytes. So I wanted to give you an example or show you how this relates very much to column choice in terms of what kind of performance you can expect from a given size column, or given length column, I should say, and the type of particle. So what you see on the lower dashed, gray dashed line is the sort of the performance you can expect for a 5 micron fully porous particle. This would be a traditional column, anything from 50 millimeters all the way up to 250 millimeters. The 250 millimeter length is not uncommon for a 5 micron fully porous particle. Then as we go up the next one to these blue and purple lines, the solid blue line and the dashed purple line, the solid blue is the 5 micron fused core particle columns, the dashed purple, the 3 micron fully porous particle. So what you see right here, and you see above it as well, is that for a given performance of a fully porous particle, the equivalent performance is a class larger particle size for the core shell, or the fused core, the fused core particle. So what you're gaining is the performance of the smaller fully porous particle column, but you're only talking about the back pressure of the larger size particle. In this case, what I'm referring to is the 5 micron. Likewise, if we move up again, to get the sub 2 micron performance, the sub 2 micron fully porous particle performance, you can use a particle that's almost as big as a 3 micron particle, the 2.7 micron fused core. Again, the equivalent performance, but at a lower back pressure because it's a larger particle. And then the top line then is the 2 micron or smaller fused core columns. So what I want to show you then is, if you look at the horizontal black dash line, that on the right side, it intersects with the 5 micron fully porous particle column, 250 centimeter length. Again, that's not unusual at all for that sort of column. But if you follow that over to the left, where it intersects or comes close at least to the 5 micron fused core column, you're even less than the 15 centimeter column, the 150 millimeter column length. So in other words, you could have a 150 millimeter length 5 micron fused core column and have equivalent or better performance than the 5 micron fully porous particle column in 250 centimeter length. So you've really cut way back on the runtime at the same, while preserving or actually slightly improving the performance. And you can keep going further to the left. Again, where it intersects the 2.7 micron, is less than the 100 millimeter column length. So you could be talking about a 2.7 micron fused core particle in a 100 millimeter length column and getting equal to or better performance than your 250 millimeter 5 micron fully porous particle column, and you may very well be able to run that certainly in an advanced instrument. And if you pay attention to really optimize the configuration of the traditional instrument, HPLC instrument, you may well get it to work quite well there as well. So this is a useful chart to show you the comparative performance of these different particle technologies related to column lengths. So then in thinking about how column selection then influences instrument selection in terms of what kind of configuration you're going to have to pay attention to, whether or not you will need to, I've divided this out into these two particle classes again, the traditional 3 to 5 micron particle column versus the 2 to 5 micron fused core columns. And if you look first on the left for the traditional particle, the 3 to 5 micron traditional particle, if, for instance, you're going to be using a traditional instrument and you want to use a 3 micron particle, you're going to very likely have to do some reconfiguration of the instrument. You're going to certainly want to look into it and check to make sure that you're at the best you can. If you're going to be using a 5 micron particle, you're good to go on any of those instruments, the traditional, the advanced, or the UHPLC. In the case of the fused core columns, let's first consider, for instance, the smallest, the 2 micron particle size. In a traditional instrument, you do not want to go there because you are going to simply have too high a back pressure, for one thing, than what the traditional instrument can likely deliver, and you're just not going to be able to, even with optimum configuration, given the generation of instrument that it is, you're not going to be able to reconfigure that to get the kind of performance that you would expect out of that small a particle column. However, if you were to use such a column, say with the advanced instrument, you're going to want to check a few things out on the instrument configuration to make sure everything's good to go. And with the UHPLC, again, it is good to go as is. The 2.7 micron, same sort of thing. To take advantage of the potential performance of that, whether it's a traditional or advanced instrument, you're going to want to take a look at the instrument configuration, which we're going to talk about here in a moment. The UHPLC, it's good to go. Likewise, then, say with the 5 micron fused core, with a traditional instrument, you're going to have to pay attention to, even with that size particle, to the configuration of the instrument. So again, if you think back to that previous chart, perhaps, the 5 micron fused core with a traditional instrument, you're going to have to pay attention to the reconfiguration just like you would with the 3 micron fully porous particle with a traditional instrument, because those two particles have very similar performance, right? So that all works together there, makes sense. With a 5 micron particle with an advanced or UHPLC, you're definitely good to go. You might say, well, why in the world would you do that? Well, we're not getting into that. The point here is simply that you wouldn't need to be concerned about any optimization of reconfiguration in those cases where you see the check marks here. So let's get into this then, and when we're talking about instrument reconfiguration, what is it that we need to do to maximize the performance of your instrument? So there are some simple modifications you can do to reduce system volume, and for all practical purposes, and I just want to emphasize that, for all practical purposes, you can think of reducing system volume as being equivalent to reducing system dispersion. Technically, it's not. I'm not going to get into that. You would certainly be welcome to contact me if you want to have further discussions, if you're curious about that. But just keeping it simple with some simple things you can do. There's 3 things that are relevant here. One is tubing length. Excuse me. And, that probably seems pretty obvious. I would say it is. Minimizing tubing length. And there's this linear relationship between tubing length and tubing volume. That's just related to volume of a cylinder. But one thing you can think about as well here is also the physical arrangement of the components of your HPLC. Sometimes these are stacked vertically, sometimes they're not. Even when they are stacked vertically, what is the sequence that they're stacked in? You want to make sure that makes sense in terms of minimizing the fluid path of the system. So you would want to, whether you're going top to bottom or bottom to top, it doesn't matter. But let's say you're starting at the top. You'd have your pump, then you'd want your autosampler, then you'd want your column oven, and then your detector. Okay, so that way you can physically get these components as close together as possible and minimize the tubing length. The next thing, which again might seem kind of obvious, is tubing diameter. It's interesting, though, that of course volume is a function of the square of the diameter. So, for instance, if you cut your diameter by a factor of 2, you cut it in half, you've reduced the volume of that same length tubing by a factor of 4. All right. So that's good, but the downside, though, is also pressure is a function of the reciprocal of diameter squared. So, for instance, if you cut your tubing diameter by half, your pressure is going to go up by a factor of 4. So that's where we have this trade-off, right? We want to minimize that volume of the tubing, but the trade-off is pressure. We can't get too high. So an ideal tubing diameter is 100 to 125 micron. So that's the equivalent of 0.004 inches ID to 0.005. And you do not want to go larger than 0.005. And that's where this especially comes in with reconfiguration, say, of traditional instruments. Those typically came with tubing of 0.007 to 0.01 inch ID, or 0.01 is 250 micron, right? Twice that of the 0.005. So that's where you may end up having to take one of those instruments and do completely replumbing with some tubing. It's not that big a deal, though. It's really pretty straightforward. Now, again, you gotta consider pressure ramifications, but the outlet, the column outlet, that is the tubing from the column to the detector, if that's not too long, it may be feasible to go to something as small as 75 micron ID. There will be a considerably higher back pressure, but again, if it's not too long, you may be able to take advantage of that volume savings as well. Lastly, the one that is potentially considerably more expensive, there's more an investment, has to do with looking at the flow cell volume. So we're talking here about optical detectors. What I'm showing you here is just sort of a cross section where you're seeing the inlet. This is the tubing, coming from the column, the inlet into the flow cell. Then the flow cell has a certain path length, and then there's the outlet, which would typically go to waste. And you have these windows on either side of this flow cell where the optical beam is passed through for doing the absorption measurement. So in traditional instruments, the flow cell volume was 10 microliters or sometimes even more. So again, if you're going to be going to fused core columns, you're going to have to be looking at putting in a different flow cell in that case. The maximum volume you want to have in there is a 5 microliter flow cell, and really the optimal is 3 microliters or less. Again, different options from different manufacturers. There's also a consideration perhaps of just the fluidics, the design of this, which is something, not all flow cells are the same. So that's going to be another factor, but it's not something that's so much in your control. Perhaps path length is, though. Of course, this is linearly related to sensitivity, right? So ideally, you'd want to keep a path length of what's sort of a standard path length of 10 millimeters, 1 centimeter. So again, two very low cost modifications you can look at for your instrument: tubing length and tubing diameter. The flow cell is very important, but that's certainly going to cost you more if you are going to be optimizing that. But again, you really can't avoid not looking at this if you're going to really want to go to the smallest particles that you could otherwise use. So the one other thing that you can't overlook has to do with data collection. And there are two parameters of data collection that software controls. This, again, is configured in the software for a method. One is sampling rate, and the other is response time. So first, let's look at sampling rate. So the top graph is sort of a true signal trace. you have a chromatogram here. But you can control your sampling rate, and that is simply how many points per unit time, how many data points per unit time the data system is acquiring. So what you need to do in order to optimize measurements, optimize whether you're looking at performance or quantitation, peak area, you need at least 10 data points across a peak. That you should consider minimum. You can go as high as 20, that's fine, that's good. I would argue more than that, and you're wasting, you're getting too large a file, you get too big a file, you're not gaining anything from that. But that's your choice. But at least 10 points across a chromatographic peak. So in the middle chromatogram there, if you will, the data points collected, the narrowest peak in this case is the first one, and then we've only got 5 data points there, which is half of what we really need. So in this case, again, sampling rate is too low. This also comes into play if you have critical pairs, right? If you're not collecting enough data points between those peaks, things can start to merge there as well. And again, as I mentioned, you want to determine what minimum sampling rate you need for your narrowest peak. So for an isocratic run, that's going to be your earliest peak. For a gradient method, it's not necessarily going to be so straightforward. You're going to have to go and look through, all your peaks and find the narrowest one to make sure you get at least 10 data points across that. And the bottom chromatogram, that's more than sufficient in terms of a sampling rate. All right, so the other downside of too high a sampling rate, or a sampling rate that's more than necessary, is going to be more noise. Okay, that's just one thing to keep in mind. Then there's the response time. Again, this is regarding optical detectors. This you can think of as how quickly the detector responds to a change in the signal, right? So what you're seeing here is sort of a worst case to illustrate the point. And when I say worst case, I mean a peak that is extremely narrow. And so what you see is in the fastest response time, which is 0.05 seconds, you're getting much closer to the true chromatographic peak there in the blue trace. But as you increase the response time, the measured signal actually looks like it's shifting later and also getting broader. Again, that's just simply from a delay in how quickly the detector is responding to the signal. And, just to say that, this was done, as it shows here, at a 20 hertz sampling rate. That's 20 points per second. That was more than sufficient for this example. But, as with sampling rate, the real downside to having a response time that's faster than necessary is you get excess noise. So again, it's something you want to have that's optimized more or less. I can tell you for an actual, real chromatogram, there's no way you need to go faster than 0.1 seconds. In fact, for 0.2 seconds may be quite sufficient. Again, that's just something you would maybe want to try and just confirm that everything looks good that way. But yeah. So, summary. What we talked about here then is instrument selection and column selection, how they're interrelated. You got to have the right instrument and instrument configuration for the type column you want to use. And that's not so much about the particle type, but the combination of particle type and particle size. And so likewise, it goes the other way. If you have, you want to use the best column you can for your instrument, you also want to make sure then, of course, that you have the appropriate instrument for that. So yeah, we talked about these column technologies, the choices and implications, the comparison of performance between the two different types. And then, instrument configuration, focused on minimizing system volume, minimizing tubing length. Tubing diameter is critical. You have to, take into account the pressure considerations as well. So again, I recommend, a 100 to 125 micron ID for that. Works very well for these fused core columns. And then also the flow cell. You want to make sure the flow cell volume is not more than 5 microliters. And we just discussed data collection as well with sampling rates. Need a fast enough sampling rate to make sure you have at least 10 points across the narrowest peak. And the detector response time needs to be fast enough as well, but again, going too fast only causes more noise and that's not anything desirable, of course. So with that, I thank you very much.
Today, my name is Tricia Schnulle, and I'm going to be taking the next minutes to walk you through some hints and tips for your cannabis analyses for your high purity water. Ultra pure water is highly prone to contamination, and as the most frequently used solvent in LCMS laboratories, its purity plays a critical role in your analyses. And so what we're going to go over today are just a few quick things you can do in the lab very easily regarding your water storage, your glassware cleaning, your consumables, and last but certainly not least, the usage of your water purification system. So, but before we dive into those tips and tricks, I do want to take a moment to discuss why having contaminated high purity water can be problematic in your laboratory. So first is difficulties in interpreting your data. If your water is contaminated, you'll end up with background noise in your chromatograms. It also can decrease the lifetime of your columns and increase the maintenance of your instruments. So we want to make sure we avoid that. But to me, most importantly, it's the risk of repeated experiments, which leads to waste of sample, reagents, solvents, and time. And we know that all of that equals money. So to save money and to save time and save your results, we want to make sure you're getting the most out of your high purity water that you can. So the first thing we're going to talk about is your water storage. And so you may not think about water storage as being an issue, but there's actually two places where you can see increased where you can experience problems, and that's actually contamination from the environment as well as contamination from the container. So these are two areas we're going to discuss over the next couple slides and demonstrate to you why these things need to be taken into consideration. The first is avoiding repeated opening of stored high purity water. So when you're storing high purity water over a length of time and you're opening the bottle and closing the bottle and opening and closing over a period of time, you're exposing it to those environmental contaminants. And so in this particular experiment, we took bottled ultra pure water and we stored it for 4 weeks, and we used it, we opened it and closed it like you would in any normal laboratory situation and to replicate that. And then here on the bottom, we just use freshly produced MilliporeSigma ultra pure water through the LCMS. And so you can see here from this top chromatogram, which is the bottled water, you can see you have some peaks and some background noise that you certainly wouldn't want to have. And you can see down here by using fresh water that you actually get rid of that background noise for your experiments. So that's storing your water and how the environment impacts it. But you may be asking, well, how does the container I actually store it in cause problems? Well, some people don't think about this, but plastic can actually be problematic for storage of your high purity water. We recommend using brown glass bottles for your storage, but people commonly use plastic carboys and things to store their water. So we've taken water and stored it in a brown glass bottle and a polypropylene bottle, and then took the water out of it and did LCMS to see what kind of results we had. And so here on the left, we have the brown glass bottle. You can see no peaks, no background noise. You come over to the polypropylene bottle, you get anti-static agent peaks, you get peaks from stabilizers, and then down here on the TIC intensity, you can see low level background from the brown bottle, but higher level from the polypropylene bottle. So you can see that polypropylene can leach agents into your water that can cause background. And so ultimately, we just want to remember when it comes to water storage, just use freshly purified water whenever possible. It will make your life easier and take out some of that questions about where some of those peaks may be coming from if it's not what you expect to see. So moving on, we're next going to talk about glassware cleaning, and the take home here is to avoid dishwashers. Is our general rule of thumb within MilliporeSigma. And so we actually, in this study, we looked at containers washed in a dishwasher versus containers washed with acetonitrile and ultra pure water. And so you can see we ran it through our analysis, and you can see here in the washed in dishwasher, you can see all these background peaks compared to containers washed with acetonitrile and ultra pure water. And we even identified some of these as Triton detergents within these peaks. And so although dishwashers are incredibly convenient, they do leave residue behind that can contaminate your water. So thus it's important to wash your glassware correctly. So just always remember your containers should be carefully rinsed to ensure that there is no detergent residue that contaminates your water. Moving on, we're then going to talk about your consumable usage, or your cartridges and filters. And of course, we want you to replace those regularly. And this is for your benefit to do this, because it can really impact your background noise and the purity of your water. We also recommend you rinse your new cartridges following the user manual instructions. In case anyone's interested, our new MilliporeSigma and IX7000 series showed here. They have consumables that can be replaced with one hand, so no more having the sign next to the system telling you how to change the consumable because it's complicated. And in addition, the user manual is actually stored here on a touch screen, so you never have to go digging through the drawer wondering where the manual is. But talking about these consumables and why they need to be changed, we're going to look at specifically final filters at this point. And so this is what a final filter looks like. It is what is at the end of the point of use. So it is like it's called, it's a final filter. And in this situation, what we studied is we studied fresh ultra pure water from a MilliporeSigma system with a filter that was relatively new. And then, or within the time range, we typically expect people to use these final filters. We actually recommend they get changed every 3 to 4 months. And then compared it to fresh ultra pure water from a MilliporeSigma system with an old final filter, and specifically 18 months old. And you may think that's crazy considering we recommend every 3 to 4 months. However, 18 months is not a crazy number. We've actually seen this very regularly in laboratories that we visited. And so this isn't a completely obscene number. And so we ran this water through a UHPLC system, and you can see the chromatogram here on the left, and you can see that with the ultra pure water with the old final filter, you get this random peak. And so obviously that can be problematic to the work that you're doing. And so the take-home point here is change your cartridges and final filters as recommended. We recommend those timelines for a reason, and the reason is that chromatogram that you just saw, that can happen to you. And then last but certainly not least, we want to talk about using your water purification system, and specifically about when you come back on a Monday from the system not being used for a couple days, or if work has been down due to the pandemic and you come back after weeks of not using it. This is even more critical at this point in time. But what we do here is we really recommend flushing the water. So in this particular study, we took MilliporeSigma Ultra Pure water on Monday after it was stood in standby over the weekend, and we ran an LCMS on it. We also took water from a MilliporeSigma system on Monday, but discarded the first 4 liters out of the system to do that flush and then have that chromatograph down here. And so when you compare these chromatographs, you can see that using the water that's in the system and not flushing it first can cause some background noise that you certainly don't want. Whereas if it's fresh water after discarding, you get no background, and that's exactly what you want to see. So as a reminder, don't forget to flush. It's incredibly important to do because you don't want to get any contaminants in your analyses. So I just want to take a moment and review what we went over. I know it's not a lot, but it's very impactful, and it's been in a short period of time. So make sure you use fresh water whenever possible. avoid dishwashers, and carefully rinse your glassware, change your cartridges as recommended, and flush your system after periods of lack of use. And so that concludes this workshop today. I hope you learned a little something, maybe can apply it to your lab. And thank you so much for your time, and enjoy the rest of your day.